Hi there and welcome to this video for Senior Physics on electrostatics and electricity. In this video we're going to explore electric fields. Now electric fields are present in all charged particles and they are defined as a region where a charged particle will experience a force upon it. They are very similar to the force fields that we notice, or the gravitational fields that we notice on the planet Earth. The only difference is that the gravitational fields that we notice only act in one direction. They only pull on an object, whereas the electric fields that you have on a charge can have the ability to push and pull. We call them attraction and repulsion. Now, an electric field works as a vector, hence we use arrows, and as we've seen previously in our vector diagrams, we have to take into account the direction that the fields happen to be acting. So just like a gravitational field, the electric fields act as radial lines on a spherical charge. A negative charge has radial lines that act into the actual charge, as you can see down in the diagram below. Obviously, for a positive charge, it's going to act in the opposite direction. So you can see that in the second diagram. The bigger the charge, the more electric field lines are going to be generated, which means that as a result, there's going to be a stronger interaction. And this interaction between these electric field lines basically generates a force. Now, as we've seen earlier, this force is basically going to be determined by the distance that those charges are placed away from each other. Now, the electric field is often given a strength, and it's given the symbol E, not to be confused with E for energy, which is measured in joules. Basically, E is defined as the force that is implied on a charge by a charge on a test charge of a specific size Q. Okay, so what force will be, so if I had a charge of 1 coulomb as a test charge, and I had a specific charge of maybe 5 coulombs, what is the force that's going to be applied upon that 1 coulomb charge, that test charge, when it's placed within those electric fields? So from this we get an algorithm which is basically made up that the electric field strength is basically equal to the force divided by the force applied upon a test charge Q. Now E is given the units newtons per coulomb. Obviously the newtons coming from the force and the coulomb being the charge of our test charge Q. Okay, so hence we get electric field strength equals newtons per coulomb. Okay, now it can be seen that as the charge moves out from as we move away from a charge, especially from a negative charge, as we move that test charge away, the amount of electric field strength will decrease, and as a result, the force will decrease as the distance increases. So as force decreases, the force decreases due to a decrease in the number of electric field line interactions. Now this may make more sense using a diagram that you can see below. So what I've got here is a negative charge. The negative charge basically has its field lines acting into the center, so they're going inwards. Now if we take the red hatched line, which is very, very close to the actual charge, you can see that there's 1, 2, 3, 4, 5 field lines which interact at this point. Now, if I move, imagine that dotted line is basically our test charge. So it has the effect of being affected by 5 electric field lines on this test charge. However, if I move away from the charge, you can see from the red dotted line to the purple dotted line, you can see that the same area only takes up 1 electric field line. So as a result, there is going to be less of a force which is going to be applied on that test charge. Another example of trying to explain this is by looking at a magnet. If you put a magnet north and north together, you'll know that hopefully that there are magnetic field lines. There will become a point where as you push the magnetic field lines closer together, or you push the poles of the magnet closer together, more force is going to be applied. However, the further away you place your magnet will result in less of a force being applied. And this is directly related to the field line interaction. Well, it's exactly the same for electric fields. The further you move away from the sort of nucleus of the charge, the less electric field lines, which means there's going to be less of a force which is going to be applied. So what we notice is this interaction between electric field lines and the force follows a specific curve, and it follows the inverse square law. Now, as you go on in your physics, you will notice that the inverse square law keeps coming up again and again and again. It's identical to the inverse square law that you notice for gravitational force as you move a certain distance away from the radius of the Earth. Every Earth radii decreases the force of gravity, and it follows this curve of the inverse square law. Well, it's exactly the same here for electric field strengths. As we increase the distance d away from the nucleus of the electric charge, the result is that the electric field lines and hence the force will decrease at an exponential rate. Okay, so as a result, we can put these observations together to form a secondary algorithm. And that algorithm is made up of electric field lines equals the constant, the force constant, times Q, the charge of the actual charge, over the distance squared. So we get E equals K, Q over D squared, remembering that K is 9 times 10 to the 9. Now, if you look at this diagram to the right-hand side, you can see that we've got a test charge, that's basically that white dot, which is going to be affected by that positive charge. Now, we're going to say that this test charge is Q, and it's going to be positive. So as we try and put Q, little q, closer to the positive Q, the result is a force is going to be applied upon it. Depending on that distance will depend on the size of that force, and Coulomb's law is applied there. However, when we want to look at the electric field strength which is applied on this object, we then have to utilize our equation kq over d squared, where obviously Q is going to be the charge of our actual charge. And this makes sense because obviously it's that actual charge, capital Q, that will determine the number of field lines that will be present a certain distance away from its center. Hence, we can utilize the equation in the blue ring, E equals kq over d squared. So what we basically get, how do we get this idea of field lines interacting? Well, you can see down below here we've got two charges which are unlike. So we've got a positive on the left hand side and a negative on the right hand side. Now if I just drew the basic diagrams of field lines, you would notice that the positive charge always has its field lines acting out from the center, and the negative charge always has them acting in. Now in the middle, where these field lines will interact, and you'll notice that they're going in the same direction. If they go in the same direction, this causes what we call attraction. There's a strong pull of these field lines to pull them together. It's exactly like putting the North Pole next to the South Pole on a magnet. They're exactly the same process, it's just this interaction of field lines going in the same direction. And there is our vector quantity that we have to look at. If they point in opposite directions, what happens then is the field lines then are going to be opposing each other because there will be like charges. The result is a repulsion will occur. Now, I can explain this repulsion with a very, very simple analogy. I've used these big wigs basically as an idea to try and understand how that repulsion occurs. Now, you'll notice that I've got like charges, positives on both sides. It will work equally well for negatives. Now what this means is that the field lines are both acting out of the center of the wig, which means that they're in the middle, they're going to be acting in opposite directions. We know that if they act in opposite directions, there's going to be a repulsion. Now imagine these wigs here are really, really spongy. They're really, really strong. So what I'm going to do is to try and push them together. I'm going to actually decrease the distance. Now, if I decrease the distance, what happens is they move close together and the hair is going to compress. Now, if that hair is really, really spongy, that compression of the hair, and remember the hair is mimicking the electric field lines, that compression of the hair is going to form a force. Because they're spongy, they're going to want to move out. So as a result, we will generate a force. Now, obviously, the bigger the hair, the more field lines, the more spongy it is, the more force is going to be generated. So as a result, you can see this interaction between electric field lines and force, and then the distance. So it's the distance decreases, the force will increase because the hair causes this force to push back, and thus repulsion will occur. Okay, so the following rules have to apply when we're looking at field diagrams. Our electric field lines are directed from positive charge to negative charge, just like we worked on in the magnets. We go from north to south. Electric field lines will enter or leave any charged surface at right angles. That basically means they act directly upwards from the center of the charge. There's no skewing of the actual vector. They're always at 90 degrees. If the electric field lines are close together or more densely packed per unit area, the force per unit charge is much higher. And that goes back to the diagram where I had that red dotted line going to the pink dotted line. You notice that if I go from pink to red, I increase the number of field lines from 1 to 5. As a result, for the same amount of area, I get an increase in force. The result is I get a greater electric field strength. So here's an example as to how we can determine the electric field strength. So in the diagram opposite, I've got two charges, A and B, which are placed at a distance of 15 centimeters. Charge A is 3.5 microcoulombs and charge B is 2.5 microcoulombs. You are asked to determine the magnitude and direction of the electric field at a point X midway between the two charges, and then determine the point between the two charges at which the electric field strength is 0. Pause the video now and see if you can have a go on your own how to solve this question. Then press play again and we'll come back and we'll solve it. Okay, I'll see you in a few minutes. Okay, welcome back. So how did you get on? Well, let's run through the first question. So we're going to determine the magnitude and direction of the electric field at point X, which is midway. Now, the first thing to understand is that we're dealing in microcoulombs. So I need to convert 3.5 microcoulombs to 3.5 times 10 to the negative 6. Also, I'm dealing in centimeters, so I need to convert them into meters. Now, X, which is midway, is going to be half of 0.15 meters, which is going to equal the 7.5 times 10 to the negative 2 meters. So what I need to do is I want to work out, let me just go back. We want to work out what the resultant electric field strength is midway. So we find the electric field strength of each of the charges. Now remember, if we go back to the initial diagram, we know that they're both positive. So one's going to be acting from left to right and one will be acting from right to left. So they're going to go in opposite directions. So let's find the charge of A, the electric field strength, at A at X, and B at X. So we use K times Q over D squared for A and K times Q over D squared for B. And we notice that for A, the electric field strength is 5.6 times 10 to the 6 newtons per coulomb in the direction of B. And for the electric field strength at B is 9 times 10 to the 9 times 2.5 times 10 to the negative 6, that's our charge, divided by the distance at halfway squared, which is 7.5 times 10 to the negative 2 all squared, which equals 4 times 10 to the 6 newtons per coulomb. And this is acting in the opposite direction towards A. So now we've got, let's say that we're going to make the direction that A is going from left to right be positive and going from right to left be negative. So the resultant electric field strength will be 5.6 times 10 to the 6, that's the field strength for A, minus, because we're going in the opposite direction, 4 times 10 to the 6, which is the electric field strength for B. The result is the overall resultant force of a charged particle at midway at point X will be 1.6 times 10 to the 6 in a left to right direction, or a positive direction going towards B. In part B, we want to know where is it going to be equal. Now, because we've got larger charges on both sides, the result is we are going to have to, the midpoint will be where the two electric field strengths are equal. So we have to make E equal on both sides. So EA must equal EB. And we've got to find the distance for that. So what we can now do is we can basically state that we've got our two algorithms, EA, which is K times Q over D squared for A, must equal K times QB over D squared. So hence that's where we get the two field lines which are going to be the same. We then rearrange the formula and the result is that we get 0.3 s squared minus 30s plus 225 equals 0. Now note for the distance for B is 15 minus s. Now we're saying that s is going to be the unknown distance. The reason for that is we've got to take s away and we're stating that s is the distance from charge A through to this point where the electric field strengths are equal. So obviously the portion which is left over from B is basically going to be 15 minus whatever s is. Now that 15 is basically due to the equation. So we're going to convert this into centimeters. So I end up, once I've converted everything, with 0.3 s squared minus 30s plus 225 equals 0. So I've now got a quadratic. So by using the quadratic formula, which is minus b plus or minus the square root of b squared minus 4ac all over 2a, I get two answers. One of the answers is 91, which is way out, so I can ignore that. So the s that's left over is 8.1 centimeters from A. So hopefully you've understood that this is quite a simple process where we just have to look on both sides. What is the field strength at both sides? And then we can apply the algorithms that we've learned. E equals F over K over Q, and E equals K times Q over D squared. If we incorporate those equations, we should be able to solve any problem. Look out on this post for some further exemplary videos where I'll run through some questions so that you have a good idea as to how to solve it. Well, I hope this makes sense with respect to electric fields. I look forward to you joining me again. Bye for now.